present British nuclear power program is based on the design of Calder Hall, which was opened in October 1956 by Her Majesty the Queen.
It is with pride that I now open Calder Hall, Britain's first atomic power station.
18 months before this, such was the confidence in the basic design that the government had formulated and published a program of nuclear power. At that time, Calder Hall was only half built. Even in the first reactor, graphite laying was still in progress. Five nuclear power stations are now being built by British industry for the electricity authorities, and 3 more sites have been selected. By 1966, it is planned that stations with a combined output of about 3,000 megawatts will be in operation. Work on the first 4 stations is well ahead. Although each group of firms has its own ideas, the general pattern is the same. British industry has cooperated to the full in the development of reactor performance from the original Calder design. At each station, the design and layout were influenced by a number of factors. The load-bearing capacity of the subsoil, for example, and care was taken to ensure that when completed, the buildings would blend with the surrounding countryside. At Hunterston, the station is sited below a hill. This is an advantage, as the reactor buildings will be somewhat taller than other stations because the fuel will be charged and discharged from the bottom of the reactors. Building the foundations and biological shields for the reactors, reinforced structures needing thousands of tons of concrete called for automatic batching plants and piped delivery of concrete on a large scale. The dimensional accuracy of construction was of the order of half an inch in 100 feet. While civil engineering was proceeding on the sites, contractors all over the country were busy. For instance, in the heavy engineering shops, the first stages in the manufacture of reactor vessels were taking place. This is one example of the advances on the Calder Hall design, where the plates used were 2 inches thick. Following this experience, the plate thickness was increased to 3 inches for all the new stations. Methods of assembly varied. At Bradwell, the plates were welded together into complete sections in a site workshop, where the precision job of cutting the holes and welding the stubs for the charge tubes was also carried out. After meticulous inspection of all welds, the sections were lifted into the reactor building by a Goliath crane. The sections will be welded together in situ, and after testing, each vessel will be stress relieved. By contrast, at Barclay, the whole vessel was built in its final position, plate by plate. As each lift was within the capacity of normal construction derricks, a Goliath crane was not needed. Was found for the delivery problem. Complete boiler shells were launched from the works and towed some 300 miles down the coast. On arrival, the boilers were hauled to the site on low loaders. The Goliath crane was used for erection, 6 boilers to each reactor. For Hinkley Point, a special jetty was built for ships to unload sections of the boilers and reactor vessels for conveyance to the site a few miles away. Although this station was started about a year later than Bradwell and Barclay, great progress has been made. The buildings are well advanced and the biological shields, complete with thermal shielding, are ready for the installation of the reactor vessels. The roof of the site workshop is in 2 parts, either of which can be removed to allow completed sections to be lifted out. All site workshops were equipped with facilities comparable with many permanent engineering shops to assist in achieving the high standard of workmanship required. The effects of the nuclear power program have spread far and wide throughout British industry. Already, the value of contracts placed for the first 5 stations exceeds £200 million, over $500 million. It is providing work for many firms. For one station alone, contracts have been placed with over 1,000 different companies. Industry is being called upon to produce things never designed before, and often under conditions of cleanliness associated more with a hospital than a factory. The fuel elements for all these stations are supplied by the production group of the Atomic Energy Authority. At their Springfields works, a large new fuel element plant has recently been completed. This plant incorporates the experience of over 10 years manufacturing fuel elements for gas-cooled reactors. While British industry is developing the Calder Hall design and making big strides forward in engineering improvements, the United Kingdom Atomic Energy Authority is looking ahead to more advanced concepts. At Windscale, the advanced gas-cooled reactor will use uranium oxide pellets, some in beryllium cans and some in stainless steel. This will overcome the temperature limitations imposed on the civil stations by the use of magnesium alloy cans and metallic uranium. The United Kingdom program has developed continuously from Calder Hall, and it is interesting to compare the reactor parameters at various stages. Outlet gas temperatures will rise from 336 at Calder to 550 centigrade in the advanced gas-cooled reactor, while mean fuel ratings will have increased by 7 or 8 times. The AGR is an experimental reactor intended to provide the information from which the last stations of the current nuclear power program will be designed. It will carry the technology of the gas-cooled power reactor another important step forward. Less than a mile away, Calder Hall has been working steadily for over 3 years. And by the end of 1959, more than 1,200 million units of electricity had been exported to the national grid. In addition, valuable experience on the behavior of fuel is being accumulated. This experience is being used to improve the fuel elements for the new power stations. A large proportion of the authority's effort is continuously directed towards the production of still cheaper electricity from nuclear power stations.